So for question 17.40, we actually have a little bit of work to do before we can start this question. We're asked to look up some information in Appendix 4, which basically provides delta H and entropic values for the different reagents in this reaction. And then we're asked to find the delta G for the overall reaction, the Gibbs free energy for this reaction. So our reaction is methane reacting with bromine to produce methyl bromide and HBr at 298 Kelvin. They already provide us the delta H and delta S for the methyl bromide. We need to look up the delta H and delta S for everything else in this reaction. And so if you go to Appendix 4, we can look up that information. We have our delta H and our entropy, and we need to look it up for methane, for bromine. They already provide us that information with the methyl bromide, and we also need to find it for HBr. So if you go to Appendix 4 and look up that information, you'll see that the delta H for methane is minus 74.87, and the entropy is 188.66. For bromine, the delta H is 0, and the entropy is 152.21. They give us the methyl bromide. We have a negative 36.4 and 245.91. And the HBr, we would look that up to see that's 36.29, and the entropy is 198.7. The units, delta H is kilojoules per mole, and the entropy is joules per mole Kelvin. Now we need to find the change in enthalpy and the change in entropy for this reaction. So we can find ultimately what is the delta H for the reaction, what is the delta S, and then we can find delta G. So our delta H calculation, we'll do that one first, right? Delta H equals the summation of how many moles and the delta H of the products minus the summation of how many moles and the delta H values of the reactants. And so if I plug in the information for this calculation, right, for my products, I have the methyl bromide. So I have 1 mole of methyl bromide at negative 36.4 kJ per mole, plus 1 mole of HBr at negative 36.29 kilojoules per mole, minus from the reactant side, just the 1 mole of the methyl bromide at a negative 74.87 kilojoules per mole. When I multiply through by moles, right, that will cancel out, that will cancel out, that will cancel out. And I can get one step closer, right? My delta H, when I add these two and then subtract the negative 74.87, I get a delta H for this reaction of approximately 2.18 kilojoules. Next, I need to do the same calculation for my entropy using the same equation, except for instead of the summation of the enthalpies, it's the summation of the entropy. That calculation looks like entropy equals the summation of what's the entropy for the products minus the summation of how many moles and the entropy that I have for the reactants. Again, I'm going to go ahead and just plug everything in that I have from the table above. So I have 1 mole of the methyl bromide at 245.91 joules mole Kelvin, plus I have 1 mole of the HBr at 198.7 joules mole Kelvin, minus the summation of 1 mole of methane at 188.66 joules mole Kelvin, plus the last one, the 152.21 joules per mole Kelvin. I didn't have room to write in the units there. We multiply through and moles cancel out, moles cancel out, moles cancel, and moles will cancel there. And then we're going to add these two together. We get our delta S equals a 444.61 joules per Kelvin minus, on the other side, 340.87 joules per Kelvin. So subtract those two, my delta S equals 103 joules per Kelvin. So now I have my delta H, now I have my delta S, now I can find delta G. Not so fast, one more step. We want to find delta G in kilojoules. So I need to convert my entropy from joules into kilojoules. So I know I have 103 joules per Kelvin, and I know that there are 1,000 joules in 1 kilojoule, so I really have 0.103 kilojoules per Kelvin. Now I can calculate my delta G. Delta G equals delta H, 2.18 kilojoules minus T, 298 K, times my delta S, which is 0.103 kilojoules per Kelvin. So when I multiply, Kelvin cancels, and then it allows me to put these two numbers together. So when I end up subtracting, I get a delta G for this reaction of approximately negative 28.73 kilojoules. So this would be a spontaneous reaction because I've calculated a negative delta G. The reaction is spontaneous because I have a positive entropy. Delta H is positive, which means it's endothermic, so that kind of counts against us, but that is overcome by the increase in entropy, the positive value of entropy that I have for this reaction of approximately 103 joules per Kelvin. So this is quite a complicated and involved problem. We had to look up those values of delta H and the entropy values from table 4. If this was an exam type question, I would just give you those values. I wouldn't expect you to have access or to go to the appendix and look up those delta H and entropy values. But it's good practice to know that it's there and know that a lot of these values have already been recorded for future use.